Okay, pre-cal 12, let's get after it. Here we go. We are now into video 14 about the remainder and the rational root theorem. So what these two things will do, well, they will allow us to continue our work of factoring our more complex polynomials. And it gives us a bit of a strategy as to determine whether or not something's a factor and also how to maybe find a potential factor. So here we go. This first bit here is all notation, but I want you to consider this here. And what I'll do is I'll kind of write it with respect to numbers next to it. So that is, you have a polynomial, so you have a function, right? So let's just say we have 2x to the 4 minus 3x cubed plus 2x minus 5. And it equals a factor, so x minus 2 times our quotient. I'm not going to write the quotient out because I'm running out of room. And then plus a remainder. Now in this case, your remainder could be 0, right? And that's what it says here. Your r is a constant or it is 0. If you have a remainder, you have a remainder. But if you do not have a remainder, if r is 0, it means that that is a factor. And we saw that when we were working on division. So what does that mean then with respect to whether or not a root is a factor? Well, consider what happens when x is 2. When x is 2, this whole thing here it's a minus a, here it would be 2 minus 2, becomes 0. So that means this entire thing becomes 0, and you just get f of a equals r. So whatever your root value is, if r is 0, then you have a factor. So if you plug in the a value of a factor or a potential factor and your remainder comes out at 0, then you know you have a factor. So you can determine whether or not a number is factorable by a value just by plugging it into your function or your polynomial. So here's an example, right? Without dividing, what is the remainder when our p of x is divided by x minus 2? So remember that p of x is equal to x minus a times our quotient q of x plus r. So when it's divided by x minus 2 means we have 2 minus 2, which means if we plug 2 in for x, we're just going to get our remainder. So that's all we have to do. We just have to solve for p of 2 because that would make that 0, right? That's my root. So p of 2 is equal to 2, and then watch your brackets here because if we get negative values, they're going to be really important. Minus 3 times 2 cubed plus 2 times 2 minus 3. So what do we get here? Well, we get 2 to the power 5 here, so 32 minus 24 plus 4 minus 3. So 32 minus 24 is 8 plus 4 minus 3, so that comes out to 9. So when we divide by the factor x minus 2, we will get a remainder of 9. Now, if you want to see that, and I'll move that over here, because what I'll do is I will show you that quickly here using synthetic division. So if we consider our function, we have 2 minus 3, we need a 0 for the x squared term, and then a 2 and a minus 3. And if we're dividing by x minus 2, 2 there, 4, 1, 2, 2, 4, 6, 12, and look at that, remainder of 9. But the remainder theorem is just a lot smoother and a lot faster than doing synthetic division. So that is how your remainder theorem can start to work. And what we can do is we can use that idea to solve for potential missing pieces of a function. So for what value of k, so k is right here, we don't know what it is, will the remainder be 5? So what that means, and when it's divided by x minus 2. So what that means is p of 2 needs to equal 5, right? When I plug 2 in for x, my remainder should be 5, but I don't know what my k value is. So we just take that and we go, okay, well, p of 2 is equal to 2 cubed minus 2 times 2 squared plus 2, but then plus k. And now you might be looking at this thinking, well, where do I go from here? But you know that p of 2 is equal to 5. We know we get a remainder of 5, so we sub 5 in there. And then solve this through, so 8 minus 8 plus 2 plus k. 5 equals 2 plus k. Subtract 2 from both sides. K is 3. So if we had a polynomial p of x that was x cubed minus 2x squared plus x plus 3, and you divided by x minus 2, you would get the remainder of 5. So we've solved for that sort of missing piece of information. So handy to do that. Now the remainder theorem comes in really helpful when you have these massive degreed polynomials, because if you just want to know the remainder, or even if you just want to know if this would be a factor, you could plug in x equals -1. So remember, because if the remainder comes out 0, you have a factor. But in this case, it's okay, well, what's the remainder? And if you did, imagine doing this using synthetic or long division, right? You're plugging in 1, but then 0, 0, 0, 0, because you need a 0 value for every single missing power. And that's just going to be a pain. So instead, since we're dividing by x plus 1, it means what's p at -1? So now we're doing -1, and see, this is where brackets and exponents are going to come in really handy, because a negative number to an odd power here, 17, is negative, but a negative power or negative number to an even power is positive. So we end up with this scenario. So we get -1 minus 2 plus 7, -3 plus 7, we get 4. So you get a remainder of 4. And that is way easier than trying to plug that through synthetic division or plug that through long division, because again, you're adding all those zeros for missing root values or missing degree values. So now let's look at how the remainder theorem ties to the factor theorem, and I've kind of mentioned it a few times, and it comes down to the fact that when the remainder is 0, we have a function. So you can determine if x plus 2 is a factor if you use the remainder theorem and your answer is 0. So let's try that. Here my x value is -2, so I'm going to try p of -2. And I get 3 times -2 to the 4 plus 4 times -2 cubed minus 3 times -2 squared minus 3 times -2 minus 10. And you might notice that I kind of zoom through these calculations, but take your time, be tedious with your step here, because -2 to the power 4, 16. 16 times 3 is 48, so boom. -2 to the power 3 is -8, times 4 is -32, so you could have switched that to negative, but we'll get to that. -2 to the 2 is 4, so minus 12, and then plus 6, minus 10. So we're just going to start adding all of this stuff together. So we have 48, minus 32, minus 12, plus 6, minus 10. So 48 minus 32 is 16, 16 minus 12 is 4, 4 plus 6 is 10, minus 10. Would you look at that? We get a remainder of 0. So that means x plus 2 is a factor, and then we could use synthetic division to start to factor this higher degree polynomial. So once we know something's a factor, we can start factoring. And that is why this all ties together nicely. Let's look at another one. Is x minus 1 a factor of the given polynomial? Well, again, x equals 1 in this case. So we are just going to try what's p of 1. Well, 3 times 1. 1's always a nice one because it's really easy with respect to our arithmetic. 1 squared minus 3 times 1 minus 10. So now we get 3 plus 4 minus 3 minus 3 minus 10. I'm not looking too confident here because this only equals 7, and then we subtract everything else. So sure enough, we're going to end up at -9. Yeah, 4 minus 3, -1, and then yeah, so -9. So we get a remainder of -9, which is no good, not 0, and it means that x minus 1 is not a factor. So that is how the remainder theorem ties to the factor theorem and helps you determine whether or not something is a factor. And we can use these things to find our factors of our higher level polynomials, which allow us then to factor them down into quadratics, which are then much easier to deal with. So here's one more. Is x minus 2 a factor? Yes, it is. So, and after I find that it's after I figure out that it's a factor, spoiler alert, I just told you, I'm going to factor it so you can see how we tie these things together. So we're going to solve for p of 2, and we're going to see if this comes out at 0. So 2 cubed minus 2 times 2 squared plus 3 times 2 minus 6. So now we get 8 minus 8 plus 6 minus 6, and yes, we get 0. So what that means, when we get that result, we can then go over to our synthetic division, set up our synthetic division. And if you're still shaky on synthetic division, watch that video again, please. And we do our synthetic division, and we get remainder of 0, which is exactly what we expect. So we get a factor of x minus 2 times x squared plus 3, right? That's my squared value, and that's my constant. I don't have an x term there. And you can't factor x plus 3 any further because it's not factorable. You don't get real number solutions. So that is the factored form of that cubic. So super helpful when we get into the graphing, right? We found all those factors so we could graph, and now this just helps you. How do you find those factors when it's a little bit more challenging? One more. In this case, we're plugging in x equals -1. So I'm not going to divide this out after the fact, but we'll just check to see if it's a factor. So -1 to the 4 minus 3 times -1 squared plus -1 minus 1. So that's 2 minus 3, whoops, quick zoom in, -1 minus 1, which gives us -5, -6, -2, -3, -1, -1. So yeah, -1, -2, -3. So we get a remainder of -3. I'm going to zoom out here, so bear with me. There we go. And that's not a factor because we get a remainder of -3. So next one. The rational root theorem is really helpful in determining, well, what roots do we even try to plug in, right? Like so far we've been given, is this a root? And you know a value to try, and you know a value to try. Well, what if you're not given any values to try? Well, if you consider factoring a quadratic, right? If you factor it out, you end up with this scenario where you get the possible factors of 3, like the leading term and the back term, right? Because if you think about how do we factor that quadratic, if you AC method it, it would be 3 as your leading value and then x as your value here. But then you would need your back values to multiply to -8. So you get a whole bunch of different possibilities. You get 3 plus or minus 1 plus or minus 8, because that'll get you a chance. But you also have the factors of 8. So you could get 3 plus or minus 2, x plus or minus 4. All of these things would give you that leading term and that back term, and it just changes the inside of your potential function. You could also have 3 plus or minus 4, and we just swap the 2 and the 4 here. That'll also result in that leading and ending term. And then we get 3 plus or minus 8 and x plus or minus 1. So then I want you to consider what are the possible factors of the last term. So you get possible factors of those numbers, right? So plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. And they go on the top of our ratio. And then what are the possible factors of my leading term? So it's plus or minus 3 and plus or minus 1. And that ratio gives you all of the potential zeros. So if you consider this spot right here, from the first one you get potential zeros would be plus or minus 1 over 3 and plus or minus 8, because that's what you could plug in for x to get the roots. Here it's plus or minus 2 over 3 and plus or minus 4. Here it's plus or minus 4 over 3 and plus or minus 2. And then here we get plus or minus 8 over 3 and plus or minus 1. So you can see that those values replicate themselves right here. What you do is you take any of those, you plug them in using the remainder theorem, and you check to see if you get 0 as a remainder. Now the important thing is, don't start with the fractions. Don't start by trying these, because man, you make your life difficult. Start with your simple numbers, 1, -1, 2, -2, and see if you get a remainder. And I'll show you, I'm going to pick one that I know is a root, but what I would do is I would try solving p of 1 and see, do I get 0, right? And then I would say, oh, it didn't, so now I'm going to try -1, do I get 0? No, I didn't. So now I'm going to try, okay, well, maybe p of -2. Well, in this case, I get 3 -2 squared plus 2 times -2 plus 8. And for remainder theorem here, you end up with 12 minus 4. Whoops. Sorry, that should be a minus 8. So you get 12 minus 4 minus 8, because that's minus 8, and you get 0. So using some of these potentials here, and I started with the easier whole numbers, I found one that gives me a remainder of 0. So then I now know that x equals negative 2 is a root, so x plus 2 is a factor, and I can start using my synthetic division. So let's do it. Find the zeros of this cubic. Well, remember, I take my factors of my last term, so factors of 12 over the factors of my leading term. So 1. It's nice when it's 1 because then we don't end up with any weird fractions as potential roots. But what are the factors of 12? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12, all over 1, plus or minus 1. So that gives me my list of factors because the plus or minus 1 just leaves me with all of the numerators. So those are my potential factors for my polynomial. So then I just start picking values to use the remainder theorem. Start with the small values because it makes your life easy. So I'm going to just start with 1. You can start with negative 1. You get to a point where you can eyeball it. You can look at how many negative values you have and how many positive values you have and whether or not a negative number is going to get the job done or a positive number is going to get the job done. But it takes time to get to that point. So I'm just going to start. Well, f of 1 is a potential root. So 1 cubed minus 9 times 1 squared plus 20 times 1 minus 12. So 1 minus 9 plus 20 minus 12. Negative 8 plus 20 minus 12. Nice. 0. So sometimes you get lucky. Right away, I get a potential, or I get a root. So then I can use synthetic division using that value. So now I can use synthetic division. 1 minus 9 plus 20 minus 12. And I'm using 1 as my root. And I know this is going to give me a remainder of 0 because my remainder theorem just got me there. And I have factored this f of x into x minus 1. And then I'm left with x squared minus 8x plus 12. And the nice part about that is once you have a quadratic, you don't have to do anything crazy anymore because you can use quadratic equation, you can use your factoring skills to break it down all the way if you can. So x minus 1, and then we get, in this case, x minus 2, x minus 6. You have found all 3 roots of our given cubic. So let's do one more here. Find all the potential roots of this. So now our last term is 6. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And then our first term is 4. So we actually get some ratio values this time. So you get this list here of now everything over 1. So you get your plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. But then you get everything over 2. But the nice thing is you could get some duplicates, right? 2 over 1 is 2, already in the list. 2 over 2 is 1, already in the list. 2 over 4 is 1 half. So, okay, plus or minus 1 half. Then we do the same. 3 over 1, 3. 3 over 2, okay, we're going to need that one. 3 over 4, we're going to need that one. And then we just got to check with 6. 6 over 1 is 6, already in the list. 6 over 2 is 3, already in the list. 6 over 4 is 3 over 2, already in the list. So that is our list of potentials. Now again, don't start by trying fractions, start with smaller numbers. Now I'm just going to tell you that when I tried f of 1, didn't work. When I tried f of negative 1, it didn't work. So then move to 2. So if you try f of 2, guess what? Doesn't work. So now I'm going to try f of negative 2. And you're going to have to do this trial by error. Sometimes you have to do that in life. Things just require trial. So 4 times negative 2 cubed plus 12 times negative 2 squared plus 5 times negative 2 minus 6. And we get negative 8, so negative 32 plus 48 minus 10 minus 6. So that is positive 16 minus 16. Yes, we get remainder of 0. So we know that f of negative 2 is a factor. So let's go to our synthetic division. 4, 12, 5, 6. Negative 8, 4, negative 8, negative 3. sorry, that's a negative. I'm like, what? That's a negative 6, 6, 0. Awesome. So we get our factored form. I'll write it right in the middle here in green. So now we get x plus 2, because x equals minus 2 is a root. And then we get 4x squared plus 4x minus 3. And you can factor that by grouping, or you can factor that using the AC method or the quadratic equation, or intuitively, and you break it all the way down to 2x minus 1 and 2x plus 3. And what you'll notice, the root here is 1/2, and it's in my list. And the root here is negative 3 over 2, and it is in my list. So they're going to be there. There's a couple minor moments where they won't appear in your list, and that's because if you ever end up with a root that is not rational, so say you have a root where x equals root 3, for instance, it happens every now and again. That is not a rational number, so it won't appear in your list, but it will appear when you do the quadratic equation, for example. So that's pretty rare that that's going to happen in the trial and practice that I give you, but just be aware of that. Like saying, well, wait a minute, I can't factor this. It doesn't work in my remainder theorem, but it's because those numbers have to be rational, which is why this is called the rational root theorem. All right, thanks so much. A lot going on there, but again, this all ties together for polynomials, and understanding these polynomial basics allow you to get comfortable graphing these things, which is key point number 1. All right. Thank you so much, and I'll see you next time.